In lecture 11, let's take a look at some of the properties that emerge from working with reactive polymers, with specific emphasis on the influence of cross-linking based on changes in process parameters, ensuing properties that evolve from there. In this particular case, you have some examples of a large range of colors and textures that can be generated with high level of internal detail through the use of reactive polymers in additive manufacturing processes. This is obtained from Stratasys. So to recap the first part of this lecture where we looked at the effects of extensive cross-linking on evolving polymers and their properties. So basically, these cross-links tend to be irreversible when they're covalent bonds. The reason they're covalent then can, the reason they're strong is because of this covalency of the bond and also because of the number of bonds that might exist between chains. As a consequence of these strong covalent bonds during cross-linking, reactive polymers compared to thermoplastics tend to be stronger, tend to be more rigid, tend to be more thermally stable, largely brittle, have low impact toughness, and lower ductility. Of course, you can make elastomeric materials with these processes as well, with these reactions, by changing the chemistry, and that can begin to bring in some more nuances in the last two properties in particular. In order to understand the evolution of properties as a function of cross-linking, let's look at this familiar plot of deformation resistance as a measure of mechanical properties as a function of temperature. Basically, as you change the glass transition temperature, you begin to have a lowering of properties and an increased level of toughness imparted into the material. So the one effect of cross-linking is basically to be able to shift this TG up and down, and so correspondingly change materials to either a more brittle nature or a more amorphous or rubbery nature. The rigidity of the chains and the impediment to motion implies that crystallinity is broken up and a lot of crystalline behavior is interrupted. In order to put in context properties of polymers relative to other material options that are there, here's a plot of strength versus density. For instance, over here you'll see that you can, for polymers in general, you can range some intermediate strengths at intermediate densities relative to foams or metals and ceramics. So that is one defining attribute. If you consider that fiber reinforced plastics are largely made by reactive materials, polyesters and epoxies, you can get a combination of relatively higher strength compared to unfilled materials through the use of fibrous reinforcements. And then they tend to compare well with what you can achieve through magnesium alloys or perhaps even some of the aluminum alloy at comparable densities. You can also see that for the other reactive materials such as silicone elastomers, you tend to be at this front over here in terms of slightly higher densities, a whole range from carbon fiber reinforced plastics down to silicone elastomers or butyl rubber in terms of what are some of the range of strengths that are possible using reactive polymers. To explore this a little bit further in terms of mechanical property distributions across the material space, here is fracture toughness plotted as a function of elastic limit. You can see low elastic limit and low fracture toughness materials in terms of foams, whereas at the opposite extreme you have metals at the higher end of the elastic limit, much higher fracture toughness. Polymers tend to populate this region over here, intermediate between foams and some of the more constructional ceramics such as bricks and stone and so on, but definitely on par with what you could get with a lot of technical ceramics in terms of fracture toughness. These are some things that are distinguishing. And again, in terms of pushing the elastic limit further out to your right, you can see that the glass reinforced plastics, epoxies, and all tend to populate the higher end of the spectrum in terms of the elastic limit before failure occurs. One thing that we looked at was that cross-linking reactions in reactive polymers tend to increase their thermal stability. This is captured in the strength versus maximum service temperature across material space. You can see that the ceramics dominate the high temperature, high strength, high temperature materials over here in this front. Intermediate service temperatures and high strengths can be achieved with a number of different nickel-based alloys in particular, and some stainless steels as well, and some refractory materials. The polymers themselves occupy this zone over here of an upper limit of service temperature below a couple of hundred degrees centigrade at best, and intermediate strengths to low strengths, 10 megapascals, right, somewhere over here. Epoxies tend to push that limit up higher um, in terms of the strength. In terms of the service temperature compared to most plastics, they tend to be further high, a lot higher than conventional plastics. In terms of thermal properties, you have thermal expansion plotted as a function of thermal conductivity. Polymers tend to be more insulating and having a higher thermal expansion coefficient. Epoxies compared to other polymers tend to have a relatively lower thermal expansion because the cross-linking really inhibits chain mobility. They tend to remain insulating unless you're adding some fillers into the material. Compared to this attribute of polymers, metals have and ceramics tend to have a much lower thermal expansion coefficient. The metals in particular tend to have much higher thermal conductivity. There are a few examples of aluminum nitride, silicon carbide that tend to be a higher thermal conductivity compared to conventional ceramics. So to recap, typical properties of polymers. In terms of mechanical properties, you have 2 to 3 orders of magnitude lower than metals and ceramics, and that is typical for reactive polymers as well. Relatively lower tensile strength, 10% of metal. This might change with addition of glass fibers or carbon fibers. Much lower hardness than metals or ceramics. In general, higher ductility, though you end up seeing a range. If you have highly cross-linked materials, you are operating below the glass transition temperature and you get brittle materials. Whereas depending upon the chemistry change and the number of crosslinks, you could have very high strain before failure and much tougher materials such as elastomers that can be generated from reactive polymers. Let us see how to take this property depiction and translate that in the context of what happens as a function of process parameters. So we have a situation where from beyond mechanical properties, if you look at specific gravity, polymers tend to generally have a lower density than metals and most ceramics. Much higher coefficient of thermal expansion, typically 10x of ceramics and 5x of metals. Epoxies tend to be lower in CTEs than thermoplastics, so reactive polymers. So much lower melting temperatures as well. And in the case of course, reactive cross-linked materials, you have degradation occurring before any melting transition altogether. Specific heat tends to be higher than those of metals and ceramics. The specific heat, which you do not explicitly explore in the plots, tends to be a little bit lower for reactive materials compared to those of thermoplastic. You also end up having a lower thermal conductivity, which can be changed with fillers, and typically these are. So now let us see how to translate the properties that we have looked at as examples into actual products by tailoring process conditions. That shall be looked at in the second part.